Here are the chapters and sections in the online textbook by William Stallings for the topics that we have been covering.
Be sure to keep up with the reading.
The reading is important for an online class. We're going to be talking about parallelism for the next couple of lectures. Parallelism helps improve performance. There are many different types of parallelism. Macro parallelism is things that you can see, things that the programmer has control over. You can write a program that has multiple threads or multiple processes. When you run multiple programs on your computer, you are doing parallel processing. There's also micro parallelism, things that you don't easily see. Pipelining, the topic of today's lecture, is an issue for micro parallelism. So are superscalar processing, which we'll talk about next time, and multiple arithmetic logic units. The instruction cycle, or the fetch execute cycle, has several steps that we've talked about before. Fetch the instruction, decode it, fetch the operands, execute the instruction, and write the results back. Imagine our simple microcode computer. If we wanted to make an enhancement to it so that it could run a little bit faster, most of the arithmetic instructions end by copying the result register onto the bus and into either of the two user registers. The next step is to copy the program counter value into the memory address register and start reading the next instruction. If we had a second bus that connected the result register to the user registers, we could do them both at the same time. We could be copying the result out of the result register into R1 and at the same time copying the program counter into the memory address register. This overlapping is the concept of pipelining. Pipelining is sort of like an assembly line where each section does its part of the work and passes the result to the next section. So we have the different stages of executing instruction. You fetch an instruction, pass to the next stage which decodes, pass to the next stage which fetches the operand, to the next stage which executes it, and finally to the last stage which copies the result back. Each stage can be working on a different instruction all at the same time, so multiple instructions can be in the process of being executed simultaneously. So there's no reason to keep the arithmetic logic unit idle when you're fetching or storing an instruction. Here's a graphical diagram from the textbook about pipelining. On the top picture, we show 4 instructions being executed by a simple processor with no pipelining. In the first one, we fetch the instruction, decode it, fetch the operands, execute it, and write it back. And after the write back is done, we start the next instructions: fetch, decode, operand fetch, execution, write back, and so forth. Each instruction happening one after the other. In the pipeline example at the bottom, we have multiple instructions overlapping each other. So while we are, imagine that time 5, we're writing back the result of the first instruction, we're executing the second instruction, fetching the operand for the third instruction, decoding the fourth instruction, and fetching the fifth instruction all at the same time. We have a simple model of execution that we use. That is, we consider each instruction is run by a conceptual control point. If you're running the debugger, you can think of the debugger stepping line by line through your program, and we expect it to execute like that. Each instruction is completed before the next instruction starts, and we execute one instruction at a time. Well, it turns out it's not really the way it happens. Pipelining violates all these assumptions, and yet we try to make it look as if the model is maintained.
Computers don't really work the way of the model.
But the system functions as if the model is true. There are some challenges with making pipeline work. In the previous examples, that was the ideal case where each thing is working independently, and each step takes the same amount of time. But some steps take longer than others. In most machines, double precision floating point divide takes more time than almost any other instruction. In particular, it takes much more time to do a double precision floating point divide than it does to do an integer add. So if you have the execution time for the divide and the execution time for the add, they're not going to be the same length. And the time to fetch an operand depends on where it is. It might be in a register, it might be in cache, it might be in RAM. So how long it takes to fetch the operand depends on its location. In order to improve pipelining, the Intel Itanium processor breaks the double precision floating point divide into 6 parts. There are 6 instructions, each one doing a piece of the divide, and that allows it to be pipelined much more easily. The decode doesn't take much time. The operand fetch is only you have to get the immediate addressing from the instruction register. The execution all happens in the AL unit. It can do an add pretty quickly. Storing the results is just putting it back into a register. But the instruction fetch requires you to go out to memory. So A, instruction fetch, is probably going to take the longest time. There are hazards which can slow down the ability of the processor to pipeline instructions. Things that can get in the way. They aren't really dangerous, but they do slow the pipelining and make it more difficult to do. There are 3 types of hazards. Resource hazards, when different instructions want to use the same CPU resource. One of them will have to wait and one of them can access the resource. There are data hazards, when 2 instructions want to access the same information. Typically when one instruction is using a piece of data and that the next one is going to want. And control hazards occur only with a jump.
Did you notice the hazard sign for falling cows?
That's a real sign taken from a real road sign. A resource hazard occurs whenever there's not enough resources for an instruction to do 2 things in parallel. For example, imagine in our simple machine we only have one access to memory. So in this example here at time 3, if we want to do an operand fetch and at the same time fetch the next instruction, we might not be able to do both of them if the operand is in memory. Typically, the instruction that is furthest along will wait, and the one that is later, if it has to use the same resource, will be delayed. In this example, we show a delay of instruction 3, where it might have started at time 3 if there was a resource available. Instead, time 3 is idle for that 3rd instruction, and it will start at time 4 when the resources are available. This is known as a pipeline stall, when an instruction cannot occur immediately and has to wait for a resource to be available. And it doesn't really harm the processing. It keeps giving the same correct instruction. It just has to wait. It slows down the processor by 1 cycle, or maybe more cycles depending on what the delay is. You can reduce the problem of resource hazards caused by fetching instructions and operands at the same time if you have multiple paths to memory. When we talked about cache memory, we mentioned that many processors have a separate instruction cache and data cache. This allows them to be fetching an instruction at one time and at the exact same time fetching data for a different instruction. Here's an example using our simple microcode machine where we show a memory address register and a memory buffer register separate for the instruction cache and for the data cache, so we could be accessing data and instructions at the same time. It's also possible to do the instruction fetch whenever the machine memory access is idle. So we keep fetching instructions and putting them in a queue inside the processor. And then when the processor wants a new instruction, it picks it out of the queue and starts passing it down through the different stages of instruction. So we're constantly fetching instructions until the queue is filled up, and we're pulling them out of the other end to execute the instructions. In order to avoid multiple hazards, you can also duplicate resources. Many CPUs will have multiple execution units. In this diagram, there are 2 integer execution units and 2 floating point execution units. So these instructions can overlap and execute multiple instructions at the same time. The answer is D, all of the above. A separate arithmetic logic unit could be used to just increment the program counter. We could have the separate data instruction cache as shown previously. And we have that second bus that we showed earlier that copies the results from the result register back to the user register.
That's been a question on exams in the past.
Students often say a second CPU, but think about how the microcode works. How would you use a second CPU without the other parts? Data hazards occur when one instruction wants to use some information that is being modified by the previous instruction. In this example, we have an add of 7 to R2, followed by a subtract of R2 from R3. Well, we have the normal fetch execute cycle shown here. In the add instruction, the result, the updated value of R2 will be written back in cycle 5, whereas in the operand fetch of the second instruction is going to be done in cycle 4. That would be before the result is written back, and therefore we get the old value of R2 without the 7 added to it. So this is a data hazard. There are a couple ways to resolve data hazards. One is register forwarding. That is, the result of a previous instruction, instead of being written directly back to the user register, it can also be forwarded to the operand fetch to the next register. Register locking is a means of avoiding data hazards, although it doesn't make it run any faster, but it keeps the instructions executing correctly. A simple example of register forwarding is shown here, where when we go to write back the data in time 5 for the first instruction, we not only write it back to its register where it belongs, but we also write it to the operand register, so it's available to the next instruction. This causes a minor stall between the decode and the operand fetch of the second and third instructions. Better register forwarding is if right after the execution, instead of waiting for the write back, instead of just writing the data back to the result register, we also write it to the operand register. And that way we don't have any additional stalls and we have the data immediately available. In register locking, we imagine that there's a flag, a 1-bit value associated with each register. When the register is in use, when it's going to be changed, we lock the register by setting the flag. If another instruction wants data from a register whose flag is set, it will have to wait until the flag is cleared. In this example, where we're again adding 7 to R2 in the first instruction, R2 is locked for steps 3, 4, and 5. When the subtract wants to use the register R2, it's locked when it goes through the operand fetch. It can't do the operand fetch until the lock is cleared at cycle 6. The pipeline processor continually fetches the next instruction to be executed. A jump instruction will change what is logically supposed to be executed next. By the time a jump instruction is executed, the processor may have already fetched several instructions thinking that the next sequential instruction is what's supposed to be executed, when in fact those are no longer valid. When this occurs, the processor has to discard those instructions that it's already fetched and fetch the appropriate next instruction based on the new jump address. Here's a diagram of an unconditional jump where the processor, as soon as it decodes and says, oh, this is a jump, has already fetched the next instruction. So it has to discard the second instruction because that's not the appropriate instruction to execute. Instead, it should be fetching instruction from the location of where the machine is jumping to. So this causes it to discard an instruction. And of course, that processing has been wasted. If you have a conditional jump, the processor may have to do some processing. It may have to check to see if two values are equal, whatever the processing is, before it knows whether there will or will not be a jump. In that case, it might have to discard several instructions. In this example, if you have to wait until cycle 4, where it finishes the processing or the execution of the instruction, by that time it may have fetched 3 other instructions, and all those instructions are the incorrect instructions to be fetched, and so they all have to be discarded. So instead of executing an instruction every cycle, now we execute one at time 1 and another valid instruction at time 5, skipping 2, 3, and 4. There are several ways you can improve control hazards. One is by branch prediction. The processor can guess which way a jump is going to go. If you have a for loop that goes through 1,000,000 times, when it gets down to the compare and trying to jump out of the for loop, if you've gone through 999,999 times, the processor can guess that it's probably going to take the jump. If it doesn't take the jump, it will just cause a slowdown. But by predicting the jump correctly, it can go faster and continue to execute what it believes will be the correct next instruction. The hazards can be resolved either by the hardware or by the software. In the Intel processors, the hazards are resolved by the hardware. Regardless of what kind of hazards occur, the processor always creates the correct result. On the other hand, there are some processors that don't avoid hazards. It is the requirement of the compiler to prevent hazards. In other words, the compiler or the assembly language programmer must order the instructions so that they don't create any hazards, particularly data hazards. In general, there's a trend towards moving intelligence to the software. Answer is C, control hazard. Using a pipeline. Pipelines are transparent to the programmer. You never see it. Your program runs correctly, at least on an Intel processor. Your program runs correctly whether you have lots of hazards or none at all. The disadvantage, though, is that if you don't understand the pipeline, you can produce inefficient code that causes lots of stalls, as opposed to if you write the code correctly, you may minimize the number of stalls. Here's an example. The original code is on the left, where we're adding x to R2, subtracting, adding y to R3, and subtracting from that. We'll assume for this case a really short 2-stage pipeline, just for the example. So they can be fixed in 2 ways. You have a data hazard in the first and second line where both R2 is used, and a data hazard between the third and fourth line where R3 is used. You can correct the problem by putting no ops in there. So we put a no op between the add and the subtract so that the processor will execute the no op, and by that time the result will be properly in the result register and it can be then used again. Another alternative is to reorder the instructions, which works even better with avoids the no ops. In the third column to the right, we reordered the instructions and avoided the pipeline hazards, at least for a very short 2-stage pipeline. Here's a more logical 4-stage pipeline. On the left, we have some code that's going to be, it adds 7 to W, adds 8 to X, 9 to Y, and 10 to Z. Well, we can do it here in the code on the left, which might be created by a compiler, generates all the instructions. You notice it always uses register 1. Well, why not? Register 1 was available. On the right, we use more registers. We use registers 1, 2, 3, and 4. So we load W to R1, X to R2, Y to R3, and Z to R4. If we have a 4-stage pipeline, by the time we get to the 5th instruction, the add, then the load R1W will have completed and we won't have a data hazard. On the left side, when you go to add 7 to R1, well, you're going to have a data hazard with the load. And when you go to the 3rd instruction, which is store R1 back into W, again, another data hazard. And the 4th instruction has another hazard because we're changing R1. But on the right, we've avoided all the data hazards.
Well, it can't be control hazards because control hazards only happen with jumps.
The improved code reduces the data hazards. If you go back and look, they both have the exact same number of instructions, but the data hazards will cause pipeline stalls, when the code on the right has no data hazards and will run much faster. There's homework assigned on Blackboard. Please make sure you upload your solutions in a readable format by midnight on Wednesday, April 8th. And keep up with the reading. Here are the different sections and chapters for the material we've been covering.